is Yifan Li from University of Akron. Title is Investigation of Artifact Phenomenon in Scanning Thermal Microscopy.
Hello everyone, this is Yifan Li from the University of Akron. So the topic of my presentation today is the investigation of the artifact phenomena in scanning thermal microscopy, SThM. Here's the outline of my presentation. We will start from the background, which includes the introduction and the applications of SThM. And for the artifacts phenomena in SThM, I will start from the literature report about the artifacts, and I will introduce the investigation of artifacts for the different systems I used, and I will provide some understandings of the artifacts from both macro and micro view. And finally, it's to summarize the conclusion. So for scanning thermal microscopy, SThM, this is a specialized variant of atomic force microscopy, AFM. And here the scheme shows the basic working principle of the SThM. It includes the topography feedback loop and the thermal feedback loop. They are working simultaneously and independently. So the function of the Wheatstone bridge is it can feedback, adjust, and balance the system in order to measure the probe's temperature in TCM mode and or maintain a constant probe temperature in CCM mode. For TCM mode and CCM mode, they are two different working modes of the SThM. TCM mode is temperature contrast mode, which we fix the supplied current and we can get the temperature distribution of the sample because it's a different thermal property of the sample. And for the CCM mode, the conductive contrast mode, is we apply a fixed temperature difference between the thermal tip and the sample surface, and then we can get a proper current distribution to reflect the sample thermal conductivity. So here for the application of SThM, based on its different properties of SThM, it has lots of applications. Like for SThM is a surface characterization method, and it can be used for the thin film thermal characterization. And based on its working principle, it can be used to do some fundamental investigation of the heat transport between the thermal tip and the sample surface. And because it's usually with the high spatial resolution, SThM can be used for the thermal conductivity characterization under nanoscale. And because SThM is a mapping method, and it can be used to map the material distribution in the composites, and also identification of the contaminant and the determination of the phase miscibility. So then I will start the artifact phenomena in the previous literature report, as shown here. The very direct reflection of the artifact is that the topography feedback has some relationship with the thermal feedback during the SThM measurement, as reported in this literature. And we can say all the literature reported this relationship, and usually it's accompanied with a higher topography feedback. A larger topography feedback signal is corresponding to a smaller thermal feedback signal, which calls the artifact. So people's general understanding about the artifact is start from the heat transfer mechanism. This scheme shows the contact situation between the thermal tip and the sample surface, and the expression shows the total heat input is equal to the heat flux of the sample and the heat flux of the contact area. So the heat flux of the contact area is defined as Q contact, which is the major cause of the artifact. This is people's understanding. And we have did some quantification of model for this polymer uniform system, as Dr. Wu mentioned before. This is the expression for the model. And we can see that the final thermal signal feedback probe current has some relationship with the thermal property, not only the thermal conductivity K, but also related to the H is the micro hardness value of the sample, and sigma is the roughness, and loading force and the slope, these other values. This part calls thermal contact resistance TCR. So we can say that the thermal feedback signal probe current is related to TCR, and this is may cause the artifact phenomena in the SThM measurement. So for our study, we began our investigation from the polymer uniform system. Here are the two systems we selected. The first one is the PDMS, with a smooth surface. And we can, if we draw a line profile for both the topography and the thermal image, we can see there is no obvious correlationship with the thermal signal and topographic signal, which indicates there is no artifacts here. And for the epoxy film with rough surface, if we draw a line profile to analyze these two images, we can see there is a negative correlationship with the thermal signal and the topographic signal, which indicates there exists artifacts in the SThM measurement. And another investigation object is we use the polymer particle composite system. Here the system is a polymer silica particle with different sizes. And here are the 3D images of the topography and the thermal image. And we did our analysis for the thermal and topographic signal for different sizes of the particle. Here 400 nanometer and 210 nanometer and 120 nanometer. For all those line profiles analysis, we can see there is a negative correlation between the thermal signal and topographic signal, which indicates there exists artifacts phenomena in these systems. And if we further decrease the particle size down to 111, there is still negative relationship between these two signals. But if as shown in this figure, these images, we can see the particle size is decreased to 40 and 35. And for the thermal signal feedback prop current image, there is randomly distributed prop current, and there is no direct correlation with the thermal signal of the topographic signal, which indicates there is no artifacts. So this may tell us that the particle size is a major influence for the artifact phenomena in the SThM. So we also investigate the line profile from the vertical direction. We can see for the 200 and 250 nanometer, there is still negative correlation with the two signals. But for the if we decrease the size to 40 nanometer, and there is no correlation with these two signals, which indicates there is no artifacts. And another investigation is that we start to investigate for the polymer. And here the line 1 is the polymer which is nearby the particle, and the line 2 is the polymer which is far from the particle. And we draw the line analysis respectively. And very interesting thing is we found a positive correlation from between the thermal signal and topographic signal for the line 1, which is which is the polymer neighbor the particle. But for the polymer far from the particle, we can see there is no correlation which indicates there is no artifacts. For this positive correlation, is this another formation of the artifacts? We don't know, so we still need to more investigation. But for my understanding is that this is like a real reflection of the situation, because as Dr. Zhu mentioned before, the particle usually has some like confinement on the polymer chain at the interface. So the existence of the particle may have may facilitate the thermal transport at the interface for the polymer. So this part, the higher prop current part, may be the real reflection of the thermal conductivity. But we still need more evidence. So here is my understanding of the artifacts. First is the microwave understanding. Case 1 and case 2 are two different contact situations based on the different sample surface roughness. For the case 1, the sample is usually shows the high roughness value. And when the tip contact with the sample surface, it will have more gaps. And for the case 2, when the sample surface is smooth enough, and there will be less gaps. So for the case 1, because of the more air gaps existence in this contact situation, there will be insufficient heat transfer between the tip and the sample surface. And according to this equation, Q total is equal to Q sample plus 2Q contact. So there will be more heat loss, and the Q contact value will increase. And compared to the case 1, the case 2, there will be sufficient heat transfer between the tip and the sample surface. So there will be less heat loss compared to the case 1. So the conclusion is for case 1, it has more possibility to generate the artifacts in the SThM compared to case 2. So the roughness value is very important in this measurement. And here is the microwave understanding. So this scheme shows the tip and the sample surface contact situation. And if at the very beginning, if you have a flat surface, when the tip touch contact with the surface, there will be less heat reflection because there is like a vertical contacting. And if the tip meet with some particle, or we call it the obstacles, the cantilever will bending and the tip will have a torsion, and there will be some angle between the tip and the sample surface. So there will be increased heat reflection. And with the further increase of the height, the tip will the cantilever will have increased bending degree, and there will be increased heat reflection. And this is verified by the following this PSPD point, which is the reflection point of the laser. And at the beginning, the reflection point is at the center, which means a good contact between the tip and the sample surface. And with the height increased, there will be the reflection of the laser, the red point will goes up, and with an increased A minus B value, voltage shows below. And with a further increased height of the sample, the PSPD point will further go increased, and with increased A minus B value here. So at the beginning, it has the normal heat loss, and with the tip meeting with the obstacles, it will generate the large heat loss and the largest heat loss. So the conclusion is the increased degree of the cantilever bending theta will contribute to the artifact. And this theta is a function of the increase of the height. So the conclusion should be the increased height will contribute to the artifacts. That is why when we have some particles, it's more easy to get the artifacts. So then the problem comes to whether the final results are influenced or not. So based on the mathematical understanding from the artifacts, here we have this equation. The Q total is equal to Q sample plus 2Q contact. So the Q sample is the reflection of the thermal property of the sample. This is what we want to get from the SThM. And the Q contact is related to the thermal contact resistance. This is what we do not want in this test, but it exists in this test. So the problem is if the Q contact is much larger or equal to the Q sample, then the Q total, the reading Q total is the reading of the prop current. It's just a reflection of the Q contact. This will cause artifacts. The Q total no longer related to the Q sample, and the reading is just the artifacts. So this will cause artifacts. And if the Q contact compared to the Q sample is much smaller, then we can say that the Q total is equal to Q sample, and the final reading of the prop current can represent the sample thermal conductivity. So the problem of this is the thermal contact resistance TCR exists in SThM measurement, and it is the root cause of the artifacts. And this TCR is related to lots of parameters like the contact pressure, roughness, and so on, like we introduced in the previous model. And it is very difficult to quantify. It's barely aim at different materials like polymer or like some hard materials. It's difficult. So here's the summary of the artifact phenomena. So for the artifact phenomena, we first talk about it causing reason is the heat loss between the thermal tip and the sample. And the reflection is the topography related thermal signal obtained in the SThM measurement. And I have provided the two solutions to solve these artifacts. First is based on the illumination of the thermal contact resistance. It can include the sample surface selecting. If we select a smooth enough sample, we may illuminate the thermal contact resistance and to get a result without artifacts. And another one is the thermal tip design. If you can design a certain type of the thermal tip which can illuminate the TCR, maybe we can get the real reflection of the thermal signal, not artifacts. And another solution is we can calculate the thermal contact resistance TCR as Dr. Zhu proposed in before. We have built a model and to calculate to get the relationship between the prop current and the sample thermal conductivity. And this is what we are doing to do the quantification model of SThM. So these are the two major solutions for the artifact phenomenon in SThM. Here's the summarized conclusion. So I have give a brief introduction and application of SThM, and the artifact phenomenon was investigated through two different systems, which is one is the polymer uniform system and the polymer particle composite system, and their corresponding understandings were proposed from both macro and micro view. And further study on artifacts can facilitate the quantification of SThM measurement. Thank you.
Okay. Open for questions.
Have you tried the power pinpoint method where the tip comes down directly vertically down and then scans by skipping, putting up and down so that it avoids any lateral force, although it does not 100% solve this tip angle problem, but it would still, I think, it would be helpful.
Okay, I will try.
Oh, so you're not aware of it?
No.
Okay, I think you should try.
Any other question?
Has any of the quantification been performed? Because I remember there was corrected data in the other talk that I assumed used some of this information.
Yes, that model is only for the polymer uniform system.
Okay.
So based on different systems, like if we want to test some hard materials, we cannot use that model maybe.
I have a short question. What is an ideal thermal chip? You should have a way to design. What would be the ideal thermal chip?
The basic principle is it can illuminate the thermal loss, the heat loss between the tip and the sample. So it may have some certain shape, like it can have full contact with the surface, sample surface.
But size still needs to be small, right?
Yeah,
So that's the challenge.
yeah.
Any other questions? If not, let's thank our speaker.